So I thought I was going to get through both IR spectroscopy and NMR in the same video, but I'm limited to 15 minutes, so you get a separate video about NMR. So here we go with NMR. Hydrogen NMR is the one that we're going to study, and you'll notice there's always the 1H in front of it over here. There are other types of NMR, and we really won't discuss any of those, but they are also very useful. NMR stands for nuclear magnetic resonance, and scientists figured out that nuclei with an odd number of protons, they can read their spin using radio waves. Now, this initially was, a really exciting form of technology, especially for medicine, because it was a way for doctors to see soft tissue and what was happening with soft tissue in the human body. And so they offered it to patients. We'd like to use this new technology so that we can see what's going on inside your body without cutting you open. And people kind of freaked out at the nuclear part. And so doctors took it upon themselves to rename it as magnetic resonance imaging, or MRI. And so if you've ever had an MRI, you've actually had NMR performed on you. But they don't call it that because patients always thought that the nuclear referred to nuclear radiation, which of course is a much, much different application of what's going on here. So MRIs are still used very commonly to, find out what's going on with soft tissue in the body. If you have, back pain, they can use it to see, if you've slipped a disc or something like that, or, if you've actually hurt part of your spine. And in organic chemistry, we use it to look specifically at the hydrogens. There are other types of NMR, particularly carbon-13, and that's what MRI uses. And that looks at those specific carbon isotopes. In this case, we're looking at the hydrogens in an organic molecule. And so when we apply an external magnetic field, the hydrogen nuclei line up according to that applied field. And if they're supplied with sufficient energy, they can flip or line up against it. And so what we really look at is how much energy does it take to flip that nucleus and make it spin the opposite direction. So here we have two different energy levels that we're looking at when we read. How much energy does it take to reverse the spin and change orientation? And how much energy did it have to begin with? And even though we're using magnets, it's radio waves that are doing the reading of the energy. So we're reading the amount of energy provided by radio waves that are needed to make the nucleus flip and change spin, and according to that applied magnetic field. And so that's what they're doing. Sometimes they refer to this as resonance, as that opposite spin. I find it very confusing because we already refer to resonance as what's happening when a double bond moves around. And so I put it here because they refer to it in the packet, but overall, I just like explaining that, we're flipping the spin and things like that, and it makes a lot more sense. Because hydrogen are present in all organic molecules, it's very useful to use for measuring information about what's happening in that molecule. And it provides information about what is around the hydrogen. So it doesn't tell us specifically about a carbon or an oxygen. It tells us what the environment of the hydrogen is. So what is close to the hydrogen, what is near the hydrogen, what is the hydrogen bonded to, all of those sorts of things, but it's all about the hydrogen atoms. So again, here's a picture of kind of what's happening inside the NMR. We have our magnets to apply the magnetic field. Our sample is here in the middle. You have radio waves coming in, and then radio receiver coming out. So you're applying the radio waves to this to see how much energy, how many radio waves are needed to actually flip the nuclei and make them spin the opposite direction of the applied magnetic field. And then that radio receiver is on the other side and is then detected. And so, as with most of these things, you know, it's a box hooked up to a computer. And then on the computer, we're having a readout of what's happening. NMR spectrums are always read against TMS, tetramethylsilane. And I realized that tetramethylsilane is not on this graph that we're looking at here. Usually tetramethylsilane is a peak, a very, very tall peak at the very end. And they've probably just left it off because it's assumed that it's there at the end of this line. And it is always marked as 0. And then everything else is measured against it. And if you notice, the right-hand side is 0. And then the numbers, the chemical shifts, go to the left. It's kind of like photoelectron spectroscopy that you learned about last year. So we're measuring how much energy it takes to the left of 0, which can be a little confusing, but that's how they're set up. So tetramethylsilane is used as the 0 mark, and it talks about that a little bit in the packet, so you'll want to take a look at that. And then all these other chemical shifts, or hydrogen peaks, are listed here. Now, one of the things that it talks about, again, a little bit in the packet, is that these peaks are not just, you know, one solid line. Often they have doublets or triplets or quadruplets against them. The nice thing about the expectations that the exam has for this course is that you're not going to be able to read all of that information, and so they often integrate all of these little peaks into one solid peak, so that it's not you trying to figure out the area underneath this curve. The height of the peak is relative to the number of hydrogens that have that particular environment. So over here, it's a little bit more obvious. We have a CH3, that's this really tall peak, and a CH2, that's this smaller peak. So it's telling us that there are 3 hydrogens with the same environment, and here there are 2 hydrogens with the same environment. And this one hasn't been integrated, so it still has the area under the curve, but you can see that this one is taller, and on the exam questions, it would be a factor of 3, whereas this would be a factor of 2. So you would see that this was 2/3 the height of this. And so you would know that this had 3 hydrogens and this only had 2. And again, you'll see that when you get to some of the exam questions. They'll show you that a little bit more specifically. This one over here, again, it hasn't been integrated, and so there are actually 5 hydrogens that all have the same environment. But since this hydrogen over here is closer to the CH2, it and its partner up here probably have a little bit different signature, and that's what's causing it to have a triplet signature instead of a single signature. So even though these 5 hydrogens are all part of this peak, they spread out a little bit like this. Again, for the purpose of our exams, they clean up that information and they'll give you one very, very tall peak that represents 5 hydrogens. And so then if the TMS is over here at 0, it's basically showing us the amount of radio waves that it takes versus the TMS to make that signature. So these hydrogens take a lot more energy than the CH3 hydrogens. Again, this is not going to give you all the information about a molecule. It's going to give you pieces of information that you're then going to apply along with the IR spectra, the mass spectra, maybe an IHD or an empirical formula, and you're going to use all of that information together to try to figure out what the molecule looks like. The one big caution about NMR that I give students, and I really wish it's specifically the IB curriculum that goes way overboard on this. In that purple handout, which is supplied by IB, it actually talks about specific chemical shifts for different hydrogens. I find that information to be completely useless and not at all helpful for the exam questions. So if it says it's a 0.9, then that means it's a CH3. Probably not. Like that really doesn't tell you anything. The important information that you're going to get from the NMR is you're going to get the relative number of hydrogens that are in a specific environment. So you know that there's going to be 3 hydrogens that have this environment and 2 hydrogens that have this environment and 5 hydrogens that have this environment. But the actual numbers along the x-axis here are, for our purposes at least, irrelevant. And again, when you study an analytical chemistry class in college, you will probably learn much more about NMR. But for the purposes of what we're doing, those chemical shifts are practically irrelevant information. And so I often tell students to ignore it, to ignore those numbers, because they're not really all that helpful when you're trying to answer questions. Please read through the packet. Please watch the spectroscopy videos on ochem.com. They go into a lot greater detail than I have here. And email me with any questions. Let me know how things are going. And try not to give Mr. Humphreys too many problems. Thanks.